Part C, visible radiation with continuous spectrum of wavelengths passes through hydrogen gas before passing through diffraction grating. A series of dark lines, that's the absorption spectrum, is produced. An interference pattern. Explain in detail why this occurs. This is an absorption spectrum. So what we're saying, visible light, continuous spectrum of wavelengths, so you've got all lambda. So you've got many different wavelengths coming through here. Here's your gas. Something comes out of it. We have a range of wavelengths coming out. Diffraction grating, and therefore you're going to get an interference pattern. So your interference pattern for a diffraction grating is sort of going to look like that. Sort of a mixture of a Young slits and or a diffraction pattern, and this for a pure diffraction grating and a single slit. If the slits of finite width, I think we've got a question on that coming up. But anyway, you've got a pattern of intensity with these sort of discrete peaks in. That's your interference pattern. And it's saying a series of dark lines is produced. So at some point, maybe we get rid of some of this stuff. Now, what I've done, let's think about this. We've got lots of wavelengths. So actually this interference pattern, the separation is going to depend a lot on the wavelength. So it won't be a series of nice little peaks like that. It'll be a much more smeared out thing. So, you know, it might be much more smeared out because you're using a wide range of wavelengths. But what it's saying is that there's a series of dark lines produced. And the interference pattern. Something like that, dark lines. Why? Well, let's have a think what's happening. Many lambda, lots of lambdas enter the gas, so the gas has its series of energy levels. If the lambdas are correct, so if HF equals delta E, so that's H, frequency, velocity over wavelength, equals delta E, then lambda is absorbed. So what's happening is that we're missing wavelengths out here. So these are then going to be diffracted by the diffraction grating, and therefore this will be, so the pattern you will get is the pattern for all wavelengths minus pattern for the missing wavelengths, more or less. So there will be bits missing. As to how that works, I'll have to think about that a bit more. what your diffraction grating is doing is splitting out wavelengths, isn't it? Because so it splits out the wavelengths because different wavelengths, you know, are going to be diffracted by different amounts. So there's your central peak, and of course everything it's central, but your first peak, there might be lambda 1 might go there, lambda 2 might go there, lambda 3 might go there. So they're all being split in different things. So if we look at just our first peak, which will be quite broad, because we've got different wavelengths, the shorter ones are going to be diffracted more. Is that right? Yep, no, the other way around. The longer ones are going to be diffracted more. Sine theta equals n lambda over d, yeah. But these are all separated out. Therefore, if we get rid of one swamp, we've got a missing area. It's a whole smooth thing, so we've got missing, move a line, implies missing bit in the peak. So what you're really doing is diffraction grating. You're looking at that, say your first peak here, first diffraction maximum, is going to spread out over the different wavelengths, because different wavelengths diffract differently, but because this has taken away wavelengths, you're going to have some but discrete wavelengths corresponding to transitions between these states. You're going to have missing points in there. Put all that in words, and you're there. A diagram like that. And this bit of the diagram, which I finally got with a bit of thinking about it, where you've got a missing wavelength, would be a good thing to include.